Hello and welcome back to this class of Inorganic Industrial Chemistry, where we are talking about the production as well as utilization of fluorine compounds. And we have started our discussion from where we see that the composition of the different minerals, because we will be talking about the natural resources. You must have the very useful natural resources in your hand, so that we can process for some useful material or compound or some other converted species. So, one of that fluorine bearing compound, because we are with this halogen, the first member of the halogen family, the fluorine. So, fluorspar is a useful material or useful mineral or ore which we can utilize for getting is different types of fluorine based compounds up to the different organofluorine compounds. So, what is that fluorspar that we have seen earlier in our previous classes, that it is the calcium fluoride. So, depending upon its different amount of content, that means throughout the globe we can have the different resources or the different places where we can go for the mineral expedition of fluorspar. So, this fluorspar may not have the equal amount of your calcium fluoride content. So, the calcium fluoride content can be different. So, since we are handling one of the major constituent of it would be the 50-50. If we consider that one is the calcium part, the cationic part is calcium and the anionic part is fluoride, from where we try to get the fluorine based compounds, even the hydrofluoric acid itself. So, directly this particular material, that means fluorspar, can be very useful for the manufacture of aluminum. How you can correlate it? If I say that fluorspar, which is nothing but your calcium fluoride, and can be utilized in the manufacture of aluminum. So, that means there should be some process where we can utilize the fluorine or the fluoride ion present in calcium fluoride to treat the corresponding aluminum ore, which is your bauxite is well known, the alumina Al2O3. So, if the Al2O3 can be converted to AlF3 or any other species, where from we can get very easily, very quickly the corresponding aluminum as the metallic aluminum part. So, you should use the fluoride ion or the fluoride anion or any other fluoride salt or even the hydrofluoric acid, which can be obtained from your fluorspar to get a production of your aluminum. So, aluminum industry basically therefore will be dependent on the availability of the fluorspar. That we will see afterwards how we can get these, the utilization of this fluorine based compound for aluminum production industrially. Similarly, we also know that while making the brick, the one of the major constituent of is the corresponding calcium oxides and calcium based material. So, the source of this calcium as calcium fluoride can be utilized for making bricks also. In a similar way, it can also be a good constituent for cement, glass fibers, enamels, and in metal working industry, that means the foundries. That means if we are going for a particular type of foundry where we can extract aluminum or any other metal, then we can take help of these anions, that means the corresponding salts you can have or the complex species you can have from the thing where we get the corresponding oxides, sulfides or any other through mining. So, that particular one can also be utilized. So, you never know that where fluorspar will be utilized for the production of say aluminum to glass fibers. So, one of the other quality is your metallurgical quality or the metallurgical grade fluorspar. Still calcium fluoride you have in your hand, which is known as metallurgical grade or med grade. So, med grade is nothing but it is having a bigger sizes of material. So, is a quartz to lumpy material or sometimes the briquetted material. We know that the coal briquette all we know. So, that sort of briquetted, so it is if it is moistened and then if you apply some high amount of pressure. So, high pressurized thing which can be your calcium fluoride, a content is up to 85%, 60 to 85% content of calcium fluoride, but you can get it in a briquetted form, and that briquetted form can be utilized for metallurgical engineering purposes, which is beyond the scope of this particular class, which is nothing but we are talking about the inorganic chemistry which can be utilized in industry. And sometimes our more useful material is corresponding utilization of this particular calcium fluoride as a flux in steel manufacturing industry. So, the steel company or the company which are producing steel, good quality steel or the iron ore, starting from the iron ore to steel manufacturing process, we use basically the flux which basically utilized for lowering the melting point and viscosity of the slag. Because we all know that the corresponding unwanted material, unwanted part from the iron, we use something, that means calcium fluoride can be utilized. So, calcium oxide, calcium carbonate and all other thing which is the unwanted material during the steel manufacturing industry or the steel industry, which can be taken away as the slag material. So, for the typical processing, that means we want to get good quality of iron, because the iron content should be higher as we go for the production. So, we should have a corresponding melting point lowering basically. So, you add the flux, that is sometimes we consider it as the fusion mixture. When we have a ore or mineral in our hand, and if we try to get a melt out of that, we add some amount of fusion mixture. And if calcium fluoride is given to it, so it is basically functioning as a flux, which basically giving a low melting point for the ore material. So, we can lower the melting point, that means your expenditure for getting the temperature, higher temperature would be less, and also the viscosity of the slag is also reduced. So, lowering in both of these two cases, the melting point as well as the viscosity of the slag, so that it is very easy to remove the slag material from the pure iron material, that is the molten iron you have in our hand. So, if the slag material is lighter than your molten iron, so it will be floated at the top of the molten iron. So, you can have some duct or you can have some exit pathway through which the slag can be removed. So, the production of slag, you can add some other additives for the production of slag material in steel manufacturing process, is dependent on the material what we are supplying as calcium or sometime as typically the calcium fluoride. So, it will be utilized as the flux material for the production of steel, as well as I told you in the previous first line, that it is also utilized in the manufacture of aluminum, because you get aluminum trifluoride or AlF3. Then we convert that AlF3 to cryolite, which is Na3AlF6. We will see also that how cryolite, so from cryolite we directly get the aluminum, how cryolite can be utilized for the production of aluminum. So, this fluorospar will therefore be dependent, we depend on this fluorospar quality, fluorospar quantity, and we can utilize it for two major industrial sector. One is the steel manufacturing sector and another is the aluminum manufacturing sector. We are also very active, our country is also very much active in manufacturing all these things. So, we are definitely dependent on your fluorospar or the availability of the fluorospar. So, if we get that aluminum fluoride out of this calcium fluoride, which is nothing, only we are simply converting the raw material as ore, what we are getting as aluminum fluoride, to convert it to typically treating the ore, that means the bauxite, and we get this one, that means the aluminum containing mineral, we have to decompose it. Where you have the aluminum containing mineral, the aluminum containing mineral is nothing but your bauxite, and that bauxite is treated with fluorospar, that means calcium fluoride and sulfuric acid. So, if we have a mixture, it can be a very high temperature one, because we do all these in the industrial reactors, not in your test tube, not in your beaker, or not in your round bottom flask. So, if we have all these things and if we put a higher temperature over that, so we should carefully look at the reaction what will be happening over there. So, that is also a very simple reaction, but sometimes the bulk of the material, the quantity of the material can also guide the reaction for a particular course of reaction, because you can have the corresponding mass action reactions. So, simply your bauxite, the third component is your bauxite, which is your Al2O3. As I told you that it treat with fluorspar have a very good amount of calcium fluoride from 60 to 85%. So, it is with calcium fluoride and then sulfuric acid. So, it is a acid base reaction which will be utilized for the production of AlF3. So, it is not that direct reaction of calcium fluoride with alumina will give you aluminum fluoride. You require sulfuric acid, because some amount of your oxygen what is available in alumina, that means 3 oxygen atoms of alumina per unit or per mole or per molecule of alumina Al2O3. So, these 3 oxygens are neither utilized for any anion formation, will be directly utilized to take out it as water molecule. So, we use protons or we use hydrogen ions as a source of heat for sulfuric acid, and that sulfuric acid is basically, so this ratio that 3 sulfuric acid will produce 3 water molecules. So, that is the simple stoichiometry of the reaction, which will tell you that how much sulfuric acid you require. That will depend on the amount of bauxite what you are handling. So, that equivalent amount of that means 3 oxygen atoms of the alumina will be taken care of by supply of 6 protons, that 6 H plus from the sulfuric acid. Otherwise, the reaction is very simple. Calcium fluoride will be converted to the calcium sulfate of sulfuric acid. The sulfate ions will be coming from your sulfuric acid. So, apart from your this med grade fluorspar, we can have another one which is known as acid spar, which is also known as like metallurgical grade is acid grade, with at least having a higher quantity of calcium fluoride, which is 96.5% by weight of calcium fluoride for the manufacture of hydrofluoric acid. Now, if you have a poor grade or lower grade of fluorspar, which is your metallurgical grade, we are utilizing it for say aluminum production through aluminum trifluoride formation. But if your content is good one, we consider it as some acid grade, because we will be utilizing these as the corresponding production of hydrofluoric acid, even if you have some amount of trapped hydrofluoric or HF in calcium fluoride. So, this spar also can be used for some other purposes, which are for making glass and ceramics. So, they have another category basically. We consider these as the spar, such that we can have the metallurgy met spar, the acid spar, now spar for glass and ceramic production or ceramic making thing. So, you have a ceramic grade calcium fluoride where content will lie between 90 and 95. So, which is less than your acid spar and is also utilized as a flux in welding. As we have seen just now that when we add the flux, it is basically utilized for lowering the melting point. So, during the welding purpose, we know that we use some good amount of the different types of flames, such as your oxyacetylene flame or any other flame. That means oxygen is being burnt with your LPG, with your CNG, with your acetylene, with your butane or any other gases. So, for that particular welding process, we know that for these cases we require a temperature above 2200 or 2400 or 2500. Sometimes it can reach up to 3000 degree centigrade or more than 3000 degree centigrade. So, if we can use some flux, that means the fusion will take place at lower temperature for that particular welding purpose, we use simply this calcium fluoride. Then a higher grade or very usefully utilized for higher calcium fluoride content material is for optical purposes. So, different optical lenses, optical material for lasers and the spectrometers we use for this, because we have to make the corresponding windows out of those glasses, sometimes the quartz glasses also. So, the glasses, for the best way of knowing it is, or remembering it is also, that sometimes we use some of these glasses as the glasses for high energy laser systems. So, you use a special quality of glass such that you use now the optical grade spar, now that optical grade calcium fluoride. So, that question can be with you also similar to that, that what sort of calcium fluoride material or the spar, fluorospar, what fluorospar you can use for making that optical grade glasses or optical grade material for say laser systems. So, this is that material which is labeled because its calcium fluoride content or the spar content is higher up to almost 99%. Then we go for another material as ore, which is fluorapatite. So, after fluorospar, if we have fluorapatite, we all know that this is also a constituent for your biomaterials, because our teeth, our bone are also apatite material. So, when we talk in terms of these apatite materials where you have selectively the fluorine is present. So, fluorine can either increase your strength of the material or decrease your strength of the material. So, the optimum concentration of fluorine is required such that you do not have the cavities in teeth. So, these are basically the fluorine material. So, that is why you use the fluorine toothpaste, the fluoride toothpaste we use, but you must know that the corresponding concentration or the available fluoride ions should be limited such that it will not degrade or decay your fluorapatite of the enamel of your teeth. So, one of the species what we can get while making or utilizing this apatite, when you have the fluorine, we consider it as the fluorapatite, which is nothing but calcium phosphate and calcium fluoride. Is a double salt again, where we are just now we are seeing that it is only calcium fluoride, but now we are bringing calcium phosphate in it. So, calcium phosphate, calcium fluoride, double salt is your apatite, and if you have the fluorine, it is known as fluorapatite. And our goal is to make the hexafluorosilicic acid, something else, where you have 6 fluoride groups or 6 fluoride as ligands. The fluorides are very good ligands, we consider it as a very small ligand system around the metal ion. So, you have, if you have the silicon center, so silicon center will be covered octahedrally by 6 fluoride groups, giving you the corresponding SiF6 anion. What is that anion and how you get the corresponding acid? That means some amount of H2, free H2 will be there. So, it is the byproduct basically what we will get it in the production of phosphoric acid from apatite, because if you look at the molecular formula of this double salt of apatite, you just simply see that we have phosphate in it. So, along with fluoride we have phosphate. So, it is possible to make both these two, that means if we are able to get it as HF or H3PO4. So, this particular material can supply you, or through the production you get it as the corresponding production of hydrofluoric acid as well as phosphoric acid. So, if you have only a very small quantity of fluorine in it, so 2 to 4% of fluorine, so digestion of apatite with 2 to 4% of fluorine with sulfuric acid. So, that will give you the corresponding hexafluorosilicic acid formation, because you have to supply silica in it, because the silica will be there. Then this fluorapatite is also an important raw material for the manufacture of different fluorochemicals. What is those fluorochemicals? Because the industrially very important fluorochemicals are there. Some of them are fluoroorganochemicals, that means the organic part is there, that means you have the carbon backbone or the hydrogen atoms are also attached to it. That means the fluorohydrocarbons, fluorine based hydrocarbons, where some of the hydrogen centers or the hydrogen atoms will be replaced by the fluorine. But what about the other species? If you consider that what other fluorochemicals you can have, so we can have one such example I can give you as the BRF5. So, this BRF5, which can be utilized for treating many material like your quartz or silica SiO2, Because just now what we see here, that you can produce hexafluorosilicic acid, that means the Si center or the silicon center on silica SiO2 has a good affinity for forming your corresponding SiF4, the tetrafluoride, silicon tetrafluoride SiF4. When it goes for the corresponding hexafluoro1, you get it as H2SiF6. So, you get this. So, this particular one, the BrF5 or BrF3 or sometimes ClF3, the interhalogen compound, which can be utilized as a good source of fluorine. So, you get it for making some very useful compound. That means, something we go for this compound that we will also see, that you have ethylene, which is nothing but C2H4 or CH2CH2, double bonded carbon you have, and on the two ends of the carbon you have two hydrogen center. And if I want to substitute all four hydrogen centers or hydrogen atoms of ethylene by fluorine, you have to think for some reaction, and that would be the most simplest fluoroorganochemicals which can be utilized for Teflon preparation. So, that we will see how you go for that utilization for Teflon preparation. So, this fluorapatite, you use it for some material, but phosphoric acid, what we have seen earlier, that making of phosphoric acid for it. Then you can use it as a source of calcium, that means for the brick making or the cement making procedures, but has been utilized to a lesser extent to get the fluorine out of it. So, if your fluorine content is less, if you do not have a good quality of this fluorapatite, you may not use it for only the fluorine based compound preparation. So, industrial exploitation of this material is still negligible. So, we can have good processes, good procedures which is industrially viable, which will be cheaper also, and you can have a very good access of the raw material. So, large scale production of fluorides basically. Now, once you make this hexafluorosilicic acid from silica as well as HF, say giving you SiF4, then SiF4 with extra HF giving you H2SiF6. So, it is possible to get the different fluorides, because this hexafluorosilicic acid, if it immediately loses the fluoride ions, it has extra fluoride content, because the silicon center can have some affinity for giving you the corresponding octahedral species, that means the hexa species, the hexafluorido species, but not the hydrofluoric acid or hydrogen fluoride. So, you can have other fluorides, the metallic fluorides, say sodium fluoride or ammonium fluoride, but this particular procedure is not very useful for the preparation of HF and that hydrofluoric acid or hydrogen fluoride as gas, because you have huge amount of phosphorus present in it. So, you have the phosphorus content in it. So, impurities which will be coming from your phosphorus compound, say phosphoric acid, make industrial processing difficult out of your fluorapatite. So, fluorapatite can be utilized mostly for calcium and phosphorus, not for your fluorine content. So, those are the limitations also. Once you know or understand all these things very easily or very nicely, we can have some comments on it, that which particular material can be utilized for making your organofluorocompounds or inorganic fluorine compounds or HF or sodium fluoride. So, we now move to your inorganic fluoride compounds. One such good example is your ammonium fluoride or sodium fluoride and elemental fluorine, that means F2 as a gas. When we go in our future classes to chlorine as well as fluorine, because you have huge demand of all these gases, that means the fluorine gas, the chlorine gas, the bromine gas and iodine, as we all know, it is also available in the solid form. So, the fluorine gas F2 and the inorganic fluorides, how we make it? So, electrochemical process we have to utilize from a salt melt. So, only from a melting thing, that means you have either the ammonium fluoride melt or the sodium fluoride or the potassium fluoride melt, which has this particular mixture is giving, is not that all other, but you just most preferred one is your potassium fluoride and HF in a molar ratio of 1:2. So, if you have 1 mole of KF, then 2 mole of HF, So, what we get therefore, if we consider that these ratios of 1:2, that means if we use it into 1:1, we get KHF2, that is potassium bifluoride as the salt. That we will also see how we make this as the potassium bifluoride salt. But when you have double amount of HF, so you have the potassium bifluoride, that means KHF2 dot HF, then it can be considered as a double salt of potassium bifluoride. But you can still use a further higher molar ratio of 2.2. So, 1:2.2. So, it is in the HF side, and at the temperature range of 70 to 130 degrees centigrade, you get this melt, and the salt melt is utilized for your electrochemical production. So, what you use? You use the electrolysis cell. So, we go for the electrolysis, as we have seen long back, for our production of hydrogen and oxygen from the electrolysis of water, we all know. So, the typical makeup of this, that means you have the electrochemical cell, because the most of the time we use this electrochemical cell, because the material what is being produced at the expense of electricity, maybe it can be a costly affair, but the purity of the material what you will be getting out of that will be highest. So, you have to have the electrolysis cell, that means it should have a corresponding anode and cathode for the production of hydrogen as well as fluorine, if you are utilizing only HF. So, if you have the melt also, as I told above, that if you have a melt of KF and HF, it is giving you a potassium bifluoride as well as your salt of HF. But if you go for the electrolysis out of that melt, the potential is set in such a fashion that only that oxidation of fluoride ion and the reduction of the hydrogen ion, if you consider HF from its electronegativity difference, H will be remain as H plus in the aqueous or the melt medium, or F will be remain as F minus. So, the fluoride ion will undergo oxidation, and H plus will accept those electrons out of these fluorides to giving you the production of hydrogen. So, this particular procedure will therefore be very useful for not only production of fluorine, but it can also produce hydrogen if we have some mechanism such that we can separate the hydrogen gas also from the fluorine gas what is being produced. So, a rating of that particular electrolysis cell is also given, which is 56.3 ampere hour. So, the cathodes what you have are utilized, and cell are used usually made of the monel alloy steel. The monel alloy steel alloys or steel make, so is a very tough container. The anodes are of different material. So, anodes are graphitized carbon. So, is a carbon based material, as we know the typical cell, the battery cells what we use, the container is something, is a anode, and the cathode is something different, which is there as the carbon rod. So, anode cathode material is important. So, you have the alloy and steel material as the cathode, or the cell itself, the whole cell can be your cathode material, and the anode is your corresponding carbon. So, on that two cases, on these two cases you get this. So, what we basically get, so you can have the corresponding, once you see what we are assembling, what we are trying to assemble around that particular cell. So, what are the materials you can have? So, you have to have the cathodic and anodic compartments. Why you are calling these as the compartment? Because the two products, like the electrolysis of water molecule, is the electrolysis of HF is also giving the fluorine and H2. But unlike O2 and H2, these two are highly reactive. So, if you just mix at a particular temperature of say around 100, more than 100 or less than 100 degree centigrade, they are highly reactive. They can again react back and combine in the form of HF back. So, you must have the corresponding separated spaces. The separation should be there. So, cathodic and anodic compartments are there, and obviously they are not separated by the use of any diaphragms, only steel skirts, something hanging from the top. So, steel skirts are suspended from the lid, that means the cover of the cell, into the melt. So, melt will be at the bottom of the cell. You have the anode and cathodes, and they are separated by steel skirts. So, when we see the flow diagram in our next class, we will now have to have good idea how these two are separated, and we can have some passages for taking out the hydrogen as well as the fluorine. Okay, thank you very much.